For over a decade, Maven had orbited Mars with near-perfect precision. Engineers and scientists considered it one of NASA's most dependable sentinels around the red planet. Its mission was straightforward yet crucial: observe the upper atmosphere of Mars, track changes, and relay vital data from rovers like Curiosity and Perseverance back to Earth. In the vast emptiness of space, reliability is everything. A spacecraft that loses orientation or drifts off course can compromise years of planning. Yet Maven had never faltered. Until one day it did. There was no warning, no gradual loss of control, no creeping software errors that hinted at something catastrophic. One moment, telemetry streamed flawlessly. The next, silence. The spacecraft simply stopped responding. Engineers checked everything remotely: power levels, thrusters, communication links, but nothing explained the sudden blackout. Maven's systems, designed for redundancy and stability, offered no clues. It wasn't a new probe still settling into orbit, nor an experimental platform testing unproven technologies. This was a veteran spacecraft, a model of consistency, suddenly gone quiet. The timing made the anomaly even stranger. Maven had just been observing a newly had happened. Was this simply aging hardware, or was something more unusual at play? One thing was clear: the story had only just begun. And as scientists analyzed the data, one question lingered, refusing to be ignored. Could 3I Atlas have done more than just pass through? The answer might be hidden in the brief, unexplained silence of Maven. A decade of stability, then a shift. For 10 years, Maven had been the definition of reliability. Its sensors functioned without interruption. Its thrusters performed predictable maneuvers. Its orbit around Mars was calculated to perfection, allowing it to serve as a communication bridge for rovers and landers across the planet. Every day, telemetry confirmed the spacecraft's health. Every month, data flowed seamlessly back to Earth. Nothing hinted at vulnerability until the observation of 3I Atlas. 3I Atlas wasn't just another celestial rock drifting through the solar system. It was the third interstellar object ever observed passing near our Sun, moving at speeds far greater than anything bound by our gravitational system. Its trajectory was unusually clean, almost surgical, as if it had been launched with a purpose. While astronomers marveled at the anomaly, Maven was tasked with collecting precise, routine observations, position, velocity, trajectory data, and context for other instruments to analyze. These were normal procedures. The spacecraft had done far more complex tasks over the years without incident. Then came the unexpected. As Maven followed 3I Atlas and collected its measurements, everything appeared nominal. Sensors reported standard readings. Thrusters performed as expected. Telemetry showed no unusual anomalies. If anyone had been monitoring live data, it would have looked like a standard observation session. But as the spacecraft passed behind Mars during its shadow phase, the calm certainty ended. When Maven re-emerged from the planet's shadow, its behavior was subtly off. Engineers noticed minor deviations in rotation that were not predicted by orbital models. Orientation, normally precise to the millidegree, had shifted. Even more subtle, there were hints of a tiny trajectory change, not enough to endanger the mission or compromise communication, but sufficient to demand attention. In spaceflight, small deviations can carry enormous implications. A whisper of a force is still a force, and every anomaly must be cataloged, understood, and explained. NASA's language around the incident was cautious but deliberate. They did not declare catastrophe. They did not claim interference. Instead, they described Maven's rotation as unexpected and suggested a possibility of minor orbital changes. These carefully chosen words highlight the unknown, a deviation from 10 years of flawless performance, coinciding with the observation of a rare interstellar visitor. Scientists could not ignore it. The sequence of events demanded analysis. Physicists and engineers faced a classic dilemma: conventional explanations could still fit. Hardware could be aging. Software glitches could appear after years in radiation-rich space. Or environmental factors such as Mars plasma interactions might subtly influence the spacecraft. All plausible. Yet the timing was remarkable. 10 years of perfect stability disrupted at the exact moment Maven observed something entirely unfamiliar. 3I Atlas, This was not evidence of extraterrestrial influence, nor proof of interaction. It was, however, a question demanding attention. In science, anomalies are never ignored, no matter how small. They are markers, guiding researchers toward the next discovery. Maven's minor deviations may have been subtle, but in the vast theater of space, subtle signals often hint at unseen forces at play. Could the brief change in Maven's behavior reveal secrets about 3I Atlas, or something even stranger lurking in the shadows of Mars? The shadow phase mystery. Maven's routine orbit around Mars had never been more predictable. The spacecraft had passed behind the planet countless times, each shadow phase carefully calculated to ensure communication loss would be temporary and harmless. Engineers always expected a brief blackout, a period when Mars itself blocked direct signals to Earth, and then a seamless return to normal telemetry. But this time the script broke. As Maven entered Mars's shadow while observing 3I Atlas, no immediate issues were reported. All systems functioned as programmed. The spacecraft carried out its observation sequence precisely, capturing the interstellar object's position, speed, and trajectory. Yet when Maven emerged on the far side of Mars, the familiar hum of data flowing back to Earth was disrupted. The spacecraft's orientation no longer matched predictions. Telemetry indicated subtle rotational shifts, unlike anything seen in its decade-long operational history. Even small deviations are critical in orbital mechanics, as they can accumulate over time and lead to larger, unforeseen consequences. NASA's statements were deliberately measured. They did not claim failure, but described the rotation as unexpected. That distinction is key. It implies that the spacecraft was neither tumbling uncontrollably nor catastrophically damaged, but had entered a state outside all modeled expectations. Engineers also hinted at a minor trajectory change, enough to prompt analysis, but not enough to pose an immediate risk. In the precise world of deep space operations, every nuance matters. A slight shift can indicate forces at play that were not previously considered, and ignoring them could compromise future missions. During this period, speculation naturally arose. Could Maven have encountered a micrometeoroid? Was there an undetected solar flare or an unusual plasma fluctuation around Mars? Perhaps a software glitch, triggered by years of radiation exposure, had caused an unexpected system behavior. These were all plausible scenarios. However, none fully account for the precise timing of the anomaly, occurring immediately after Maven's observation of a rare interstellar object, 3I Atlas. The coincidence was difficult to ignore, especially for a spacecraft that had maintained flawless performance for over 10 years. Scientists emphasize that correlation is not causation, yet timing is rarely irrelevant in physics. Every variable matters, and interstellar objects like 3I Atlas are unique. They bring histories shaped by entirely different stellar environments, radiation exposures, and magnetic fields. Even if inert, their presence introduces factors that have never been tested within our solar system. When Maven exhibited unplanned rotational shift just after tracking such an object, it created a puzzle that demanded careful scrutiny. The shadow phase became the focal point of curiosity. While hidden behind Mars, Maven operated without real-time oversight. Whatever caused the anomaly happened in silence, invisible to engineers on Earth. That period of uncertainty is precisely where discovery often begins. Minor anomalies, quiet deviations, or unexplained behavior can illuminate physics not yet understood, even if they never escalate into dramatic events. Was Maven's brief disorientation simply a mechanical fluke? Or did 3I Atlas leave an imprint on the spacecraft, subtle yet undeniable, data, uncertainty, and the unknown? After Maven re-emerged from Mars' shadow, engineers faced a problem that defied immediate explanation. Telemetry confirmed that the spacecraft's orientation no longer matched its expected trajectory. Every previous orbit had been precise, predictable, and consistent. Now subtle changes had appeared, changes that did not trigger alarms but could not be ignored. Small as they were, in deep space operations, even a minor deviation is significant. Physics treats these shifts as data, not opinions, because every force, no matter how faint, leaves a measurable trace, NASA responded cautiously, emphasizing that the spacecraft was not in danger and that all systems were nominal. Yet the carefully chosen words revealed the unspoken reality. Something occurred that the models could not account for. A decade of stability had been interrupted in a single orbital pass. Engineers and scientists began to ask questions about the events surrounding the anomaly. Could a residual electromagnetic field from 3I Atlas, accumulated over its interstellar journey, have affected Maven? Could interactions with Mars's plasma environment have amplified this effect? Or was it simply a case of aging hardware combined with a perfectly timed coincidence? This moment highlights the tension between expectation and uncertainty in space science. Spacecraft like Maven are designed to be reliable, almost unimaginative in their operations. They orbit silently, methodically, and follow decades of tested models. Their mission depends on consistency. That is precisely why this deviation stood out. It was not dramatic or catastrophic, but its subtlety made it more compelling. Engineers rely on decades of patterns to identify failures quickly. Glitches follow familiar signatures: sensor resets, power dips, communication delays. Maven's behavior matched none of these. The anomaly forces scientists to confront the limits of current knowledge. Interstellar objects such as 3I Atlas are not well studied. Their paths, compositions, and magnetic histories are largely unknown. Unlike asteroids or comets from within the solar system, these objects have traveled through vastly different environments, carrying influences that may subtly interact with spacecraft, planetary atmospheres, or magnetospheres in ways we cannot yet quantify. While most interstellar travelers probably have negligible effects, the precise coincidence of Maven's rotation change immediately after observing 3I Atlas cannot be dismissed. Lightly, researchers emphasize that uncertainty is not a weakness in science, it is its fuel. Observing the unexpected, recording it, and asking rigorous questions allows models to improve. The data from Maven's Anomaly, paired with ongoing monitoring of 3I Atlas, provides a rare opportunity to study interactions between our spacecraft and objects of completely alien origin. Even if no direct causal relationship is ultimately found, the event underscores the need to remain attentive to anomalies, however small or brief. Could the quiet deviation in Maven's behavior hint at a hidden property of 3I Atlas, something that challenges our understanding of interstellar physics? Or is this simply a coincidence too precise to ignore? Patterns, anomalies, and scientific vigilance. When anomalies like Maven's rotational shift appear, scientists are trained to focus on patterns. A spacecraft operating reliably for over a decade develops a statistical history, a record that informs every future prediction. Deviations from this record are never treated casually. They are flagged, investigated, and often lead to improvements in hardware, software, or operational protocols. But in this case, the anomaly coincided with Maven's observation of 3I Atlas, an interstellar object moving at speeds and on trajectories that defy the patterns of the solar system. This intersection of a perfectly predictable system with a rare, unpredictable visitor demands attention. Engineers reviewed every possible mechanical and environmental factor. Thruster firings, reaction wheel performance, sensor readings, and communication logs were examined in minute detail. Yet nothing in the spacecraft's design or history suggested a reason for the change in orientation. The rotation was subtle but real, outside the model expectations, and it occurred precisely after the observation window of 3I Atlas. It was a puzzle that resisted easy explanation, a reminder that in space the extraordinary often appears within the ordinary, hidden beneath layers of routine. Meanwhile, scientists turned to the interstellar visitor itself. Atlas is not just unusual because it comes from another star system, it carries a history that is entirely alien. Its structure, composition, and electromagnetic properties are unknown. Even small residual effects from its journey through interstellar space could interact with local plasma or magnetic fields in ways we have yet to understand. This is a realm where assumptions, however reasonable, must be questioned. Assuming passivity for every interstellar object is practical, but it is not conclusive. Science thrives on testing such assumptions, especially when empirical data presents something unexpected. The broader lesson is that anomalies, even subtle ones, can be powerful catalysts for discovery. They force scientists to ask questions they might not have considered, to test models more rigorously, and to confront the unknown. In the case of Maven and 3i Atlas, the sequence of events may ultimately prove mundane: aging components, software quirks, or minor environmental fluctuations. But the timing and specificity of the anomaly make such explanations insufficient on their own. In science, coincidence is not proof, but it is a reason to look closer. Every detail counts. Telemetry logs, orientation history, orbital parameters, and timing windows are all pieces of a larger puzzle. And in a system as complex and precise as deep space operations, even the smallest unanticipated factor can provide new insight. Observing, recording, and analyzing these subtle deviations is how science advances. While headlines may favor dramatic discoveries, the quiet inconsistencies, the brief moments when expectation diverges from reality, often hold the keys to deeper understanding. As Maven continues its orbit and 3i Atlas speeds away into the cosmos, could the whispers of a subtle force be the first hint of an entirely new kind of interstellar interaction, one that challenges what we thought we knew about physics beyond our solar system? The subtle forces behind the silence. When a spacecraft like Maven deviates unexpectedly, scientists instinctively search for causality. In deep space, forces that seem insignificant can accumulate to produce measurable effects. A tiny misalignment in a reaction wheel, a fleeting software hiccup, or a sudden plasma fluctuation can ripple through a system. Normally, engineers have designed redundancies to absorb these variations. But the anomaly in Maven was not just a minor blip. It was an orientation shift that didn't match any known mechanical or environmental factor, and it coincided precisely with the observation of 3i Atlas. The timing was too exact to dismiss. Physics is unforgiving but precise. Every force leaves a trace, every interaction a signature. That's why anomalies like Maven's are treated as data points rather than isolated curiosities. Scientists ask, what was different at this moment? The answer, at least in part, was 3i Atlas, a visitor traveling at interstellar speeds, carrying with IT conditions magnet. IC histories and plasma interactions entirely unknown to our solar system. Could such a distant object influence a spacecraft indirectly, perhaps through subtle gravitational perturbations, minor electromagnetic effects, or even previously unconsidered plasma interactions? The possibilities are speculative, but grounded in physics, not imagination. Engineers combed through the mission data meticulously. They ruled out solar storms, asteroid impacts, or debris interference. The spacecraft had not performed any unscheduled maneuvers. Communications and telemetry followed predictable paths until the blackout phase behind Mars, which was standard procedure. Then, when Maven emerged from Mars's shadow, the spacecraft's orientation no longer aligned with its expected trajectory. This is the type of quiet anomaly that doesn't make headlines but can fundamentally challenge assumptions about deep space operations. The situation also underscores the limitations of our knowledge regarding interstellar objects. Unlike asteroids or comets native to our solar system, 3i Atlas does not follow gravitational patterns that have been observed and cataloged for decades. Its internal structure, composition, and any residual electromagnetic effects are unknown. In essence, it is a variable that no model has fully accounted for, making its observation simultaneously rare and scientifically invaluable. The spacecraft's brief disorientation is not proof of a direct interaction, but a compelling reason to ask more precise questions about these visitors from the stars. What makes anomalies like Maven's compelling is not sensationalism, it's the subtlety of the signal. Science progresses when researchers notice deviations from expectation, no matter how small or temporary. Each detail, the angle of rotation, the timing of the blackout, the proximity to 3I Atlas, adds a piece to a puzzle that could refine our understanding of interstellar physics and spacecraft resilience. And while conventional explanations are likely, the timing remains tantalizing. A decade of flawless operation interrupted at the exact moment a rare interstellar object is under observation. Could the seemingly insignificant silence of Maven, paired with the fleeting passage of 3I Atlas, be hinting at interactions we have yet to comprehend, forces so subtle they whisper rather than roar, yet could reshape our understanding of the cosmos? The unseen variables of deep space. Space is not empty, even when it seems so. Beyond the vacuum and distant stars, there are electromagnetic fields, charged particles, plasma streams, and radiation belts, all interacting in ways that are often subtle, often unpredictable. For a spacecraft like Maven, these interactions are typically minor, accounted for in simulations, adjusted for by software, and mitigated by redundant systems. But when an interstellar object such as 3I Atlas enters the local environment, a new, poorly understood variable is introduced. Unlike objects native to our solar system, these travelers carry with them physical histories shaped by entirely different stellar environments. Their internal structure, charge distribution, and magnetic fields could be completely foreign to our models, and their influence, though likely faint, cannot be automatically dismissed. The anomaly in Maven's behavior is emblematic of how physics confronts the unknown. During the shadow phase behind Mars, the spacecraft experienced a subtle rotation that was inconsistent with its years of data. There were no external collisions, no thruster activations, no significant radiation spikes. Nothing conventional could account for it. Yet the timing aligns almost perfectly with Maven's observation of 3I Atlas. Scientists do not jump to conclusions about causation, but they do pay attention to correlation, especially when that correlation is precise and immediate. In this case, the anomaly serves as a marker, pointing to conditions and forces that may be overlooked in conventional models. What is remarkable is the contrast between the spacecraft's decade-long stability and this brief, unexplained deviation. For 10 years, Maven functioned flawlessly, relaying critical information from rovers like Curiosity and Perseverance without incident. Orientation, rotation, and telemetry were predictable. The sudden change underscores a fundamental principle in space science. Even a small deviation in a system built for precision can carry significant implications. It forces engineers and scientists alike to consider edge cases, rare events, and variables that lie outside of typical operational experience. 3I Atlas, moving at interstellar speeds, is inherently unpredictable. Its passage reminds us how limited our observational sample is for such objects. Unlike solar system asteroids, we have not tracked its evolution over billions of years within our gravitational well. Its interactions, both direct and indirect, with spacecraft, magnetic fields, or plasma environments, remain largely theoretical. And while it is unlikely that this single object would destabilize a well-engineered spacecraft, the possibility cannot be ignored. Each observation, anomaly, and minor shift provides data that could refine models, improve predictions, and prepare humanity for future encounters with interstellar visitors. The Maven incident emphasizes patience in science. It is not about sensational claims or dramatic conclusions. It is about documenting, analyzing, and questioning anomalies where they arise. Even a momentary silence, a slight rotational shift, or a brief telemetry gap becomes meaningful when viewed against a decade of flawless operation and the appearance of a rare interstellar object. Could the subtle rotations and quiet deviations observed in Maven be nature's way of revealing hidden interactions between our spacecraft and these mysterious cosmic wanderers, hinting at forces that our equations have yet to fully capture, silent clues, and the limits of observation? One of the hardest realities in space science is how often the most critical information arrives quietly. The loud events, the collisions, bursts, and explosions capture attention immediately. But sometimes the most revealing clues are subtle. A pause in communication, a tiny rotational drift, a brief anomaly in telemetry. Maven's behavior after observing 3I Atlas fits this pattern. There was no catastrophic failure, no dramatic alert, only a deviation from expected orientation and a potential minor orbital shift. Yet these silent clues are precisely what scientists value. They hint at interactions that models may not fully capture. When a spacecraft has spent a decade operating predictably, its data becomes a standard against which anomalies are measured. For Maven, that standard was exceptionally stable. Every orbit, every maneuver, every transmission over 10 years adhered closely to expectations. Engineers could rely on its predictability. And then came the observation of 3I Atlas. The timing was exact. Maven conducted its monitoring, recording the interstellar visitor's passage, and passed behind Mars as part of routine orbital motion. Only after re-emerging from this shadow phase did its behavior diverge from the norm. Such precision in timing cannot be ignored in physics, even if the cause is mundane, a hardware issue, software glitch, or environmental fluctuation. The alignment of events demands scrutiny. What makes this scenario particularly intriguing is the lack of immediate explanation. In the vastness of space, countless variables affect a spacecraft. Plasma interactions, solar wind fluctuations, minute gravitational influences, all are known factors. Yet the only new variable during Maven's brief anomaly was 3I Atlas. It did not need to make contact, nor exert a force within traditional expectations. Its mere passage introduced conditions previously unobserved in our local environment. The anomaly itself, small and fleeting, represents an opportunity to test assumptions about interstellar interactions. Could there be subtle electromagnetic effects carried across light years? Could high-speed passage near a planetary magnetosphere induce rotational effects, however minor? The truth is, current models cannot fully answer these questions, which is why careful analysis of even minor deviations is critical. NASA's handling of the incident illustrates scientific discipline, cautious language, careful acknowledgement of unexpected rotation, and open-ended investigation. There is no leap to sensationalism, no premature claim of interstellar influence. Instead, the approach is methodical. Collect data, compare it against predictions, and remain aware of variables that do not fit neatly into existing equations. The anomaly, though quiet, is meaningful precisely because it is unanticipated, precise in timing, and connected to an extraordinarily rare observation. In the end, this is a story of patience, of observation, and of respecting the unknown. It reminds us that exploration is not just about discovering new places, but also about recognizing where our understanding is incomplete. Each anomaly, however subtle, is a potential window into a deeper truth about the universe, especially when rare cosmic phenomena like 3I Atlas are involved. Could the quiet anomaly in Maven's rotation be the first hint of an entirely new class of interactions between interstellar objects and our solar system, waiting silently for science to decode them? The journey continues and questions persist. As 3I Atlas continues its journey through the solar system, the questions it raises remain very much alive. The object itself moves swiftly, almost imperceptibly against the backdrop of stars, yet its passage has created ripples in the data that scientists will be analyzing for months, perhaps years. Maven's brief anomaly is now catalogued, discussed, and debated, but it is far from fully understood. The spacecraft continues its mission, sending data back to Earth. But every scientist involved is acutely aware that even a small deviation in a decade-long pattern carries potential significance. The quiet moments, the subtleties in the numbers, may carry more weight than any single dramatic event. It's easy to dismiss anomalies as minor, unimportant, or coincidental. Engineers are trained to look for common causes first: component wear, software bugs, external interference. These explanations are usually correct. Space is harsh, and spacecraft experience countless micro-events that never make headlines. But the context here is what makes Maven's situation unusual. A decade of flawless operation suddenly disrupted during the observation of one of the rarest objects humanity has ever encountered. That alignment cannot be ignored, no matter how much one wants to classify it as just another glitch. Science, at its core, exists to investigate these moments, to test assumptions, and to confront the edges of knowledge with evidence. 3I Atlas itself is a reminder of the limits of our understanding. Born around another star, shaped by different magnetic fields, radiation environments, and plasma conditions, it carries a history entirely alien to our solar system. Its speed, trajectory, and physical composition are unlike anything we normally study. Any interaction with local space, even one as subtle as a change in a spacecraft's orientation, provides a rare glimpse into physics operating under conditions previously inaccessible to direct observation. Every micro-effect, every data point, is a puzzle piece that may help refine our understanding of interstellar mechanics. The broader lesson here is humility. Humanity has cataloged countless solar system objects, simulated their paths, and predicted their behaviors with impressive accuracy. But when something arrives from outside this familiar environment, the rules may shift subtly, forcing a reassessment of what is considered predictable. Maven's brief deviation may never be linked definitively to 3I Atlas, or it may prove entirely unrelated. Either outcome is valuable. Both paths teach caution, attention to detail, and the necessity of remaining open to new information. In the end, science is never about certainty. It is about continuous observation, hypothesis, and refinement. 3I Atlas will continue its quiet voyage, and Maven will continue its orbit around Mars. And the questions it leaves behind, the anomalies, the patterns, the small inconsistencies, are exactly where the next discoveries often hide. Could the seemingly minor anomaly recorded by Maven hint at forces or interactions we've never before observed, silently rewriting our understanding of interstellar travel? The unfinished story of Maven and 3I Atlas. As 3I Atlas slowly moves beyond the solar system's inner boundaries, the mystery surrounding Maven remains unresolved. Scientists continue to analyze telemetry, orientation data, and environmental conditions during the critical moments when Maven entered the shadow of Mars. Every piece of information is scrutinized, every anomaly cataloged. Even tiny deviations, imperceptible to most, are now under a microscope. In physics, small signals can point to profound truths. Sometimes the quietest events, those that almost go unnoticed, carry the weight of major discoveries. The anomaly itself, a subtle shift in rotation, combined with hints of a minor orbital variation, is not catastrophic. Maven is fully operational, continuing its mission around Mars. Yet, the timing is what keeps researchers cautious. A decade of flawless performance disrupted immediately after observing an interstellar object cannot simply be brushed off as coincidence. Science thrives on curiosity, and in this case, the questions are louder than the answers. Was Maven influenced by a previously unconsidered physical effect? Could 3I Atlas, with its alien history, have interacted with Mars's plasma environment in a subtle but detectable way? These questions remain open. Interstellar objects like 3I Atlas are exceedingly rare. Only a handful have ever been observed, and each one challenges assumptions about what is possible in our local cosmic neighborhood. They are travelers shaped by conditions entirely foreign to our solar system. Their passage offers a natural experiment, a fleeting chance to study physics under unusual circumstances. Maven's brief anomaly may be nothing more than a coincidental hardware or software hiccup, but it could also provide data that reshapes how we understand the interaction between interstellar matter and planetary systems. The uncertainty itself is a scientific opportunity. This episode underscores a fundamental truth about space exploration. Even when we think we understand a system, the universe has a way of surprising us. Models, predictions, and simulations are incredibly useful, but they are always built on assumptions. When something or someone arrives that doesn't fit those assumptions, we are forced to re-examine everything. That is the essence of science. Maven's anomaly is not a headline-grabbing disaster. It is a reminder of how fragile certainty can be and how essential observation, patience, and open-mindedness are when exploring the cosmos. And so, the story is not over. 3i Atlas will depart, continuing its silent voyage through the galaxy. Maven will keep orbiting Mars, gathering data and relaying it back to Earth. The anomaly will remain a subject of study, a subtle whisper challenging scientists to think beyond conventional boundaries. Each dataset, each model, and each observation contributes to a more complete picture of both the spacecraft and the alien interstellar visitor. The truth, when it comes, will likely be as quiet and understated as the anomaly itself. Final. What hidden truths might 3i Atlas reveal, not through dramatic displays, but through subtle nudges and quiet anomalies, hinting at forces and interactions humanity has never before imagined?